Hey guys, welcome to our last section of organic for this semester. We're entering into something called molecular spectroscopy. Molecular spectroscopy is the experimental process of measuring which frequencies of radiation are absorbed or emitted by a particular substance, and then attempting to correlate patterns of energy absorption or emission with details of molecular structure. In essence, we're trying to figure out, why do we draw things the way we draw them? How do we know that they have 7 carbons in a line or in a ring or anything like that? We are determining structure with molecular spectroscopy. We're going to talk about 3 different kinds of spectroscopy: infrared, nuclear magnetic resonance, and mass spectrometry. Today, we're going to focus simply on infrared spectroscopy. Infrared spectroscopy and all your other spectroscopies deal with something called electromagnetic radiation. All of the instruments that you will use are based on the utilization of this radiation. Remember that light is described in terms of a particle and a wave. We're looking here at the wave. There are 2 different terms that we use to talk about waves of light and of energy. Wavelength is the distance between 2 peaks, while frequency is the number that pass a given point in a certain amount of time. So if I'm looking at 1 second, so I look at how many pass this point, and that's my frequency. Now, obviously, these are things that you cannot measure without the help of instrumentation. This is the electromagnetic spectrum. You've probably seen this before in both physics and introductory science in high school. Frequency and wavelength are inversely proportional. So wavelength, you can see here on the bottom, and frequency. So as frequency goes up, wavelength goes down. So high frequency, low wavelength. High frequency, short wavelength. Low frequency, long wavelength. These are both related to energy, and the reason that wavelength and frequency are inversely related is because wavelength times frequency equals the speed of light. They are inversely proportional to each other. Energy, on the other hand, is defined as h nu, where nu is frequency and h is Planck's constant. So inversely related wavelength and frequency are both related to energy. So if you look at gamma rays, for example, high energy, high frequency, short wavelength. And the converse is true on the other side. Molecular spectroscopy focuses on different regions of the electromagnetic spectrum. Infrared deals with, of course, the infrared region. UV vis, or ultraviolet visible spectroscopy, deals with the center here, the UV and the visible light. And radio waves are used in nuclear magnetic resonance spectroscopy. Nuclear magnetic resonance spectroscopy deals with the difference in nuclear spin states. IR deals with vibrational states, and UV vis, which we will not talk about in this class, deals with electronic transitions. This is what a typical IR spectra is going to look like. So you have percent transmittance on your y-axis, and typically you will only see wave numbers on the top of your x-axis where these micrometers are. Your textbook shows you both micrometers and wave numbers, but you will typically see wave numbers in most of what you will work with outside of this textbook. There's 2 distinct regions of the IR spectra that are important. So the region from about 1450 to 500 is known as the fingerprint region. This is unique for every compound. It also tends to be very messy, very dirty, and so we don't look at it a whole lot in this class. The remainder of the spectrum going this way is known as the functional group region. And that makes sense because IR is very useful in helping you determine and identify functional groups. This might look like a backwards graph to you. You're used to seeing peaks coming from the bottom and going up. Here we refer to these as peaks. So they come from the top and drop down, but those are what we consider peaks in an IR spectra. IR takes advantage of different vibrational states. So think about a molecule. You know it's not stationary, right? It is always moving around, and temperature can increase that or decrease that, but it's always moving, and it's moving in different directions. So put your arms out and you can see symmetric stretching. So that goes both arms in, both arms out. You can have asymmetric stretching, where one arm comes in, the other one goes out, one comes in, the other one goes out. You can have bending vibrations as well as stretching vibrations, and these all have differing energies, which is why they show up differently on an IR spectra. Scissoring is similar to symmetric stretching, but instead of coming forward with your arms, you go up and down with your arms. Rocking is going one direction with both of those bonds. Wagging, small motions, like you're at a rave, and twisting, of course, around and around. These different vibrational states are what result in a different IR spectra for each molecule. Each functional group has characteristic vibrations at certain frequencies. So for example, you'll see these when we get to them in a few slides. Alkanes typically have peaks at 2850, 1450, 1375, and 1450. Now, these are average numbers, okay? Everything can shift just a little bit. Do not take this as it has to be at 2850, otherwise it's not an alkane, okay? They will show up at about the same spot, but electronegative atoms and other things can shift it just a little bit. This is a general representative area in which you will see peaks for alkanes, alkenes, alkynes, and arenes. I will give you a copy of this in class so that you can use it to help identify functional groups in these IR spectra. These are your characteristic frequencies for things that have C double bond O's, and that's a very characteristic frequency that shows up at about 1700 wave numbers, or Cm-1. You can see in all of these, you get a C double bond O stretch in the 1600 to 1700 region. And again, depending on what it's attached to is where it's going to show up in that region. But if there is a C double bond O in your molecule, you will have a peak at about 1700. A few other carbonyl group molecules, acid anhydrides obviously have two carbonyl groups, and so they will show up at two different frequencies. Nitriles show up closer to the end of your spectra, and there are others that you will see. Not all of them are included on this list. So let's take a look at a few examples. So this is decane. It's an alkane. We'll draw it out here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all of those carbon and hydrogen bonds can move and stretch and vibrate and bend based on the type of light that you give to the molecule. So if you irradiate it with IR light, it's going to bend and stretch and give you this spectrum. Every time you have a CH bond, you will get CH stretching in this about 3000 wave number region. You will also get bending for both alkyl and CH2 groups around the 1500 and the 1300 region. If you see those two things and nothing else, you are probably dealing with an alkane. Now, of course, from here over is our fingerprint region that we largely ignore. But if you see no other peaks, it is typically an alkane. Alkenes are similar, but they have a little bit more. So again, you see this characteristic CH stretching, and you see the CH2 region there. The difference is that obviously your fingerprint region is much more convoluted than the last one we saw. But the other one that's very important to see is that C double bond C stretching at about 1680 wave numbers. Now that is not a C double bond O peak. Okay, that's a very important thing to recognize here. You'll see C double bond O peaks here in a little bit. They are much taller, much longer peaks, and so that's the distinction you can make between those two. Octine is a alkyne, and you can see that the fingerprint region again is very convoluted. You see your CH stretching here in both of those. The big difference here between this and our alkene is the C triple bond C stretching at about 2100 wave numbers. Toluene is an aromatic molecule. So aromatic molecules have something that we do look at in the fingerprint region. These CH bendings only show up there if it's aromatic. You do see the C double bond area again, because there are 3 double bonds in an arene. Now, what you don't see is 3 double bonds, right? You only see one characteristic peak for a double bond, and you see this CH stretching again. Alcohols are very distinct on IR spectra. This peak right here is what we consider very broad. Okay, this here would be a sharp peak, but this is a very broad peak for the OH. The reason for this is because the oxygen-hydrogen bond stretching gets kind of lumped together with that carbon-hydrogen bond stretching and bending that you saw in previous slides. If you see a broad OH band, you have an alcohol somewhere on your molecule. It does not tell you where on your molecule, but it does tell you that you have an alcohol. Now, what does tell you if you have it in a primary, secondary, or tertiary position is part of the fingerprint region. This is, again, something we will not look a whole lot at, but it is very useful information if I give you something and you need to decide where to put the alcohol and all I give you is the IR. Now, that's unlikely to happen. I will give you an IR, an NMR, as well as other information to help you solve a problem. But you know, looking at this, that there is an alcohol as a functional group in your molecule. Ethers are distinct in that they have this CO stretching, and this is also present in esters, but esters will have another C double bond O bond. You see again that CH2 bending and stretching here and here, but the distinction here is that you have the CO stretching of an ether. Here's an aromatic ether. So you get your CH stretching, and then you have 2 different CO stretchings here. That's not because there are 2 CO bonds, it just shows up in 2 different places. This is an amine. Amines are unique in that they have a double peak down here for primary amines. You also see the CH2, CH3, and the CH stretching here. Aldehydes and ketones, as well as all of your carboxylic acid derivatives, are going to have this strong absorption peak at about 1700. That is characteristic that you have a C double bond O in your molecule. Now, where that C double bond O goes, you'll have to figure out with other methods of spectroscopy, but this helps tell you that there is a C double bond O. And again, you see that CH stretching, that CH2, CH3 bending in the appropriate regions. Carboxylic acids have both a C double bond O and an OH. And as you can see, the OH and the CH2, CH3 peaks get really messed up in carboxylic acids. Now, this is considered a broad peak, but it is it is distinct from an alcohol, mostly because you also have the C double bond O, noting that this has to be a carboxylic acid. And of course, carboxylic acids have to go on the end of a molecule. And so you know it's going to have to go there. You still have the characteristic CH2, CH3 bending and stretching. And again, the fingerprint region, less helpful in our case. Other derivatives of carboxylic acids are also going to have a C double bond O. Esters, for example, will have another CO stretch because of that carbon-oxygen bond right here. And you will almost always in every molecule see carbon-hydrogen stretching as well as bending. So what are you looking for in an IR spectrum? Well, you're looking for the identity of functional groups. What I will do is give you a molecule for IR. I'll draw it out for you. And what I want you to do is match that molecule with its appropriate IR spectra. You want to look for characteristic peaks. Now, on the ACS exam at the end of the semester, you will not have a table, a chart, anything to look at to determine what things could be where in an IR spectrum. That being said, your exam for me, you will get to use that information. So you don't need to memorize any of this information. However, the more you work with it, the more you will memorize certain things just because you've been using it. For example, there's a C double bond O at 1700. I know that because I've worked with it enough. I know that OHs show up as broad peaks. I know where the C H stretching and bending shows up because it's in almost every spectra. You will get used to using the same things over and over the more you do these. You also want to look for what's there as much as what isn't there. So if there's no peak at 1700, you don't have a C double bond O, and you can kind of cross things off your list in terms of what functional groups might be in this molecule. In class, we will be working on some problems in groups. We will take our time working through what IR looks like and how to match molecules with their IRs. And then next time, we will move into nuclear magnetic resonance spectroscopy, which gives us a lot more information and can be coupled with IR to give us even more information.